with the main aim of course, producing energy which is affordable, accessible, user-friendly, and sustainable. That is the big question, like this, what are low-tech energies? That is the amenable energy we require. What is socializing now this low-tech to the communities? Because the focus was to provide, affordable energy to the people, which they can be able to generate and which they can be able to use. Okay, so those are the elements we are looking at. Now we've been able to mainstream the biogas systems to the communities. There's an uptake. Over 30 people have been able to uptake the energy, and of course we now want to come up with another scheme of providing energy to the communities using what we term as renewable energy cooperative societies. Already we are developing one pilot plant. This funded by CNRS. This is a French organization. So there we are. There are several other studies which are ongoing. And there you are. Thank you.
Thank you. Thank you, Dr. Aloysius. Any questions?
Thank you very much for your presentation. I was curious. I want to have a question is, have you done the economic analysis about the low-tech solutions, energy solutions? Because I was wondering what's the cost and the long-term benefit will we get from using these low-tech energy solutions? Thank you.
Yeah, I take you back to that slide because the moderator was on my case. That is why I jumped that. Now, one of the main objectives of this kind of research activities is to ensure energy access and affordable energy to the people. So it should be low cost. Actually, low tech is supposed to be translated to low tech, low cost energies. That is our main focus. That everybody should be able to reach out to this kind of energy, be able to use the technology to produce their own energies, and at the same time, of course, produce it affordably. That was the main objective. That is why we are looking at that.
Any question? So, no question. So let's thank Dr. Aloysius again for sharing his work. So next speaker, we have Dr. Liu, Guicai Liu.
Thank you, Ian. Okay, good afternoon, everyone. My name is Guicai Liu from Nanyang Technological University, Singapore. My topic is about waste to energy with chemical looping strategy. Because of, as we know, Singapore is a very, very small city, very fine city. So actually, the land in Singapore is very, very precious. So the waste must be treated before it landfill. It has no land to landfill. So we must do something on the waste. Okay. So let me introduce a little bit about our institute. Our institute is Nanyang Environmental Water Research Institute. Newly, we did research work on a lot of environmental issues like biotechnological bioprocess, environmental, water recovery, resource recovery. Actually, what we are doing is mostly on resource recovery. So let me introduce a little bit about the chemical looping concept. This is a way to convert the fuel, especially solid fuel or gaseous fuel, into the energy or the chemicals. Usually, here we take it, chemical looping combustion as the example. Here, for example, if we have fuel and air, if we mix them together, then we can directly combust. But if we separated them, we use a solid material as the intermediate, then the fuel can be oxidized by the lattice oxygen in the oxygen carrier. So actually, this process is a separated process. So we can separate the fuel, separate the air with the fuel, so the products can only have CO2 and water that are easy to be achieve CO2 removal, CO2 capture after it condenses. This kind of process actually it can be extended to other process. For example, we can achieve partial oxidation like gasification or reforming. Here we can also achieve to obtain the nitrogen-free syngas. Also can we have benefit of the catalytic partial oxidation and high reactivity to syngas. We can also integrate this process with other process, so we can achieve hydrogen production and CO2 capture. So essentially, this process is a product inherently separation process. With this process, we can achieve a lot of functions. So, but in this technology, there will be a lot of challenges. One of the main challenges will be the oxygen carrying material and the reactor design. Here, I will introduce more about these two issues. So, if we want to treat MSW, the solid municipal solid waste, because the waste has a lot of chloride, for example, from the PVC. So we have to deal with the chloride. Otherwise, there will be severe dioxin and boiler corrosion. And with the also, if the syngas is from nitrogen-free, then it also can achieve CO2 capture. Here is our process. We compared to the conventional CLC, we have a separated solvent generator, so you can separately generate the solvent after oxidized. Here we demonstrated oxygen carrier with a solvent composite material, so we can achieve HCl removal and the solvent is regenerable. Here we use iron ore modified with the different alkaline earth metal like barium, strontium, and calcium. Here we found actually the barium and strontium has much more high efficiency on the separation of the chloride. But when we compare different material, actually it's the same conclusion. Heavier alkaline earth metal have better separation efficiency. After that, because at the beginning we use iron, the conversion efficiency would be low for the fuel. That here we use copper. Copper would be a better material for fully conversion of the fuel. Here we use barium or strontium, copper oxide, magnesium oxide, and aluminum oxide. We run 20 cycles. At least we see the stabilize that it can separate it successful. And because of the copper, the melting point is quite low. That will be an issue. That will be an issue if we operate the oxygen carrier in high temperature. So actually the copper will be migrate outwards on the surface after many cycles. That it will cause severe sintering. But if we have additive like alkaline earth metal, here we found the copper will not be migrated at the surface. So the sintering issue will be mitigated. And also the reactivity, if we have alkaline earth metal, the reactivity would be better and it's, much more stable. And because of the sintering of some material, some of the bulk, very big particles will be generated, and it's not possible to use in the fluidized bed. After this, we also did oxygen carrying material with other resource like solid waste resource like ferry sludge, because the sludge is actually from the water treatment sludge, because we use ferry chloride in the water treatment. Then we can utilize the ferric, the iron, as the oxygen carrying material for the process. And we run maybe around 100 cycles and performs stable. Another process we are doing is to convert the solid waste and also capture CO2 and utilize the capture CO2 in the reforming, so we can simultaneously capture CO2 and utilize the CO2 to generate syngas. Also, we have utilized the biomass or the MSW, this kind of solid fuel. Here, we found if we don't have any solid fuel at this reformer, actually the first cycle it has a little bit CO2 capture efficiency, but after that, there's almost no. That means there's no regeneration if we don't have solid fuel. But if we have MSW or biomass, we see the CO2 conversion efficiency around 70 to 80%, and the MSW is much better than the biomass. So, and about the reactor, we designed the reactor for the chemical looping process. This is our co-model, and this is our hot model. We use the reactor with 3 reactors, so the oxygen carrier, the reaction material can fluidize and transport it between these 2 or 3 reactors. Here we run the experiment in lab-based gasifier and CLC system. Probably this work is a little bit complicated for the successful operation. Probably we need something new technology like machine learning to optimize our material and the process and our operation. That's all my sharing. Thank you very much.
Thank you, Gui Chai. So, any questions?
Thank you very much for your presentation. The idea to generate energy from the waste is very great, and you have demonstrated the possibility to generate energy from the waste. So I have a question. What about, according up to now, the proportion to generate energy from waste are not very high in the whole energy proportion. So what do you think is the major obstacles to turn this technology into large scale application? Thank you.
That would be a complex problem. One of them is the reaction material, as the reaction material will be very easy to be agglomerated and sinter, that it will block the normal operation in the long term. Another is the abrasion that will be cause the many costs of the oxygen carrier, and also there will be some contamination from the abrased oxygen carrier powder. That would be a big issue, I guess.
Okay, thank you.
So any other question?
Have you done the economics?
Economic? That's a very good question. We did a very brief economic because we want to avoid the corrosion of the boiler. Essentially, if we just compare, that would be probably comparable, but it depends on what's the condition and what's the scale.
All right, thanks for that.
Thank you.
But I mean, chemical looping, a really good idea.
Thank you.
But have you considered other things like plasma incineration? I mean, you have fewer problems. Of course, I mean, the economics may catch you, but you seem not to have issues with the money.
Yes,
so
yes.
Perhaps you could consider.
Yeah, this kind of new things always have this kind of issues.
No, what's the skill for your pilot project? Every day you will deal with how much waste?
Oh, this one is just a prototype. Just a prototype, lab-based prototype. It's the waste is, I don't remember the waste, but the gas of the syngas is around 10 to 20 liters per minute. Just a prototype lab-based per minute.
Okay. Now let's thank Dr. Liu again for sharing his work. So
Thank you.
next speaker we will hear from Dr. Lucia. Let's give him a warm welcome.
Good afternoon already. So thanks for the opportunity. So yeah, I'm going to talk about a little bit about. Oopsie. Huh? Doesn't want to move.
Oh, this is next.
Okay. About biocatalysis in the beneficiation of biomass, and the previous speakers basically make my talk a little bit easier because it seems people do know about biotechnology, and so I can go through the slide very easy. So biocatalysis that we are using, so we use microorganisms and enzymes to actually catalyze our reactions instead of metals or of the old harsh chemical methods. So with biocatalysis we use a much lower temperature, normally ambient. There's no pressures. We can often, most of the time, work in aqueous environments, but if the substrate is not soluble, then we can also go into organic solvents. In our group, we always couple green chemistry with biocatalysis because there's no ways that you can do everything with biocatalysis, especially when you get to the workup. So yeah. When you look at the 12 principles of green chemistry, which is a big topic these days, we find that biocatalysis basically adheres to at least 10, if not to all 12 principles, because we can use biomass and we do it sustainably, very little energy input, and all the other principles that's of interest. So like I said, in our group, we basically combine biocatalysis and green catalysis. And again, yeah, just there is no high pressures, no temperature, high temperatures. The energy input is really minimal, and yeah, we do need to combine it with green catalysis, especially on synthesizing some of the substrates, and also to do the downstream process. So these days, there's actually huge demand for green technologies. Especially, you know, everybody wants to have a lower carbon footprint in the next few years, and you also want stuff that's very environmentally friendly, or not at least damaging the environment. And especially in Europe, they're very, very strict on these things that these days, that if you put something on your skin or you ingest it, that they want a greener process or greener natural products going in them. So often you can extract these from the environment, from plants and whatever, but the yields are normally very low, so your cost is very high. One of the examples we have in our group, THCV is one of the cannabinoids in your cannabis, but in such low concentrations, it's got really excellent applications. But if you want to extract it from cannabis, the price is $310,000 a kilo. we actually came up with a process to do it with green chemistry that dramatically reduced the price. Yeah. So I'm just going to give a few examples of what we do in our group with biocatalysis and biomass. So we're really good or great on circular economy projects. One of them being around citrus. So just in South Africa, we found that we have about 1.7 million metric tons of just oranges, and 60% of that goes to waste. Same with the lemons. So at least 50% of lemons goes to waste. There's a lot of areas in Africa that a lot of orange growing regions. So yeah, the waste is really, really great. So we actually take every part of the orange, for instance, or the citrus. And if we start, for instance, on the outer part, so you've got all your essential oils in the outer part. And a company approached us, they called AP Bio, and they asked us to do something for them to have come up with a natural insect repellent or insecticide. So insecticide meaning that it actually kills the bugs. So by using an enzyme cocktail, we took this essential oil from the citrus and we made a new product which they called Nude a Bug. And we also made another project, nude ketone. Now, nude ketone you normally find is the active ingredient of grapefruit. But to extract 1 kilo of nude ketone, you need about 4,000 grapefruit. So it's not very economical. Now, nude ketone is really an excellent compound. It's got a lot of applications. But one of them is that it's actually insecticide. So it kills, for instance, your mosquitoes. So after we've developed this process for this company, they took it to Tanzania to a company there. So they developed what they called long-lasting mosquito nets. So they impregnated the nets with this nude ketone. And they found, apparently if they put it in the middle of the room, this net, the mosquitoes just goes to the furthest corner. And if it actually gets in contact with the net, it dies. So they do have a application with the WHO, and they hope to get approval by December to actually then get this into the market. The other one was a project for biodex in South Africa. So we actually take the juice of the citrus fruit and we combined it with a chemical stabilizer, and there was actually an enzyme in the juice that then did this reaction with a stabilizer, and it actually then came up with a efficacy much more efficient than if you just have the two components on their own. So they've got all these different certifications, and they also registered this the two projects or products in the EU. They're already producing on ton scale. And also during COVID, they found that within seconds, if they clean the surface within seconds, it basically kills 99.9% of the virus. If you look at the citrus again, the white part, the albedo, that normally contains your pectin. Pectin is used to make jellies and jams, but you need up to 85% of sugar and a low pH to get this gelling to take place. We took the normal pectin and we added an enzyme, and we then made low methoxypectin. And low methoxypectin basically only needs calcium to gel. So you can now use these products then for people with diabetes. They also use it as a filler in some of the pharmaceutical products. And they also found that it's excellent for metastasis of cancer, so that the cancer does not spread to other parts of the body. Just this, I threw this in, and it comes down to the same work that has been presented. So we basically also started with biomass, got the sugars out, converted to with HMF with another very green process, and then we found a microorganism in horse manure that can actually produce FDCA directly from the HMF. Then one of the another project that we did was for a company called Kepri. So we all know that's huge amounts of paper and pulp waste everywhere in the world. So South Africa has done quite good on recycling. Maybe it's not as good as some of the other developed countries, but yeah, even after recycling, there's a lot of this short fiber waste, and they don't really know what to do with this. So they brought it to us, and especially in South Africa, in the rural areas, there's a lot of farmers in summer. If there's a lot of rain, that's fine, but if it's drought or during winter, they actually do not have feed for their ruminants. So we actually came up with a process to take the waste paper and pulp, make some products out of that. So some of it then being sugars that they can add to the feeds at a concentration of about 10%. But then the remaining, we actually make some fibers from there that they can use as a filler. And we also remove the lignin so that that can be used in additional products. One of our flag projects was this Oris butter. So Oris butter is one of the very, very expensive products used in fragrances. So basically they take this flower, this Oris flower or iris flower, they normally put the roots away for 2 to 5 years under specific conditions, and then this Oris butter fragrance basically develops. But the problem is, you know, you need a lot of space to put those roots away for 2 to 5 years, and we've seen it ourselves. The slightest conditions that's not good for the roots, then you find that fungus is growing on the roots. So we actually came up with a process at the CSIR. We found a very, very low-costing enzyme, and the enzyme can actually then produce this flavor and or this fragrance within 40 hours instead of 2 to 5 years. So we've now licensed it to a company in South Africa in the Cape to commercialize this. So another one is extraction of ferulic acid. Ferulic acid is actually used in a lot of applications, especially sort of supplemental. It's an antioxidant, anti-inflammatory. And you get it a lot from woods and grasses and so on, but it's not very available because it's bound to a lot of carbohydrates. So what they normally do is they add sodium hydroxide and they boil it, and eventually it comes off, the ferulic acid. But you basically destroy the bran completely. So we actually came up with a single enzyme from the baking industry that can do this, and within a few hours you basically get your ferulic acid, and because you do not destroy the bran, you can also then use that additional product for animal feed. Another, my final one here is ambrafuran. So Firmenich actually got the same product, or they are the leaders. They called it Ambrox. So Ambrox is used in the flavors and fragrance industry as a fixative. So it fixes your very expensive perfumes and essential oils, so that you can have a longer lasting product. So initially they got this fragrance from the excrement of sperm whales. Nobody knows who was the first one to think, let's see what's in this stuff. But in any case, so it basically would drift on the sea, and oxidation takes place, and eventually you get this fragrance. But the people then started hunting the poor sperm whales to get these chunks before they actually excrete it. So they had to come up with this treaty to prevent it from being happening. And so then people came up with chemical ways to do it. And it's basically now done in 8 chemical steps. But it's really harsh chemicals that they use in very harsh conditions. And when they do discard the waste, they have to do it in special ways to not damage the environment. So we actually came up with a microorganism that can cut out 7 of the 8 chemical steps, and we also came up with a final green chemistry step for the final cyclodehydration of the intermediate diol. And if we do then plant the sclarysage plant, which is the source of the sclareol for the starting material, we can also create some jobs in South Africa. So This is basically the comparison between the chemical process and our process. So we only have 2 steps. Our overall yield is about 90% versus the chemical one, which is not more than 60%. We have no harsh chemicals. We recycle everything. Our temperatures are low. Our waste stream is environmentally benign, so you can basically just take the growth medium, autoclave it and then discard it, or you can even dry it and use it as animal feed. And yeah, so we basically patented this process and then optimized it afterwards. So yeah, this is just a few examples of what we do with biomass at the CSIR. Thank you.
Thank you, Dr. Lucia. So we have time for 2 questions.
Hello, very nice talk. I wonder about the pyrolysis of the biomass, because the biomass generate a lot of different kinds of products. Do we need a lot of separation process after pyrolysis?
We don't do any pyrolysis in our group, but we do have a group in Durban called BIDF, and they actually do pyrolysis. So apparently there you get all kinds of products. But I mean, yeah, it is a high temperature process, but we never actually do it in our group.
Dr. Lucia again for sharing his work. So I think that's our last presentation of the sections, and I would like to thank all our speakers for his insightful contribution, and all of audience and the interesting questions. And the session is now concluded, and have a good rest of the conference. Thank you. Thank you, everyone.